All right, only 2 questions left. I know everyone's upset with this chapter. Did go by fast-ish, but definitely messy. So without further ado, we do have to talk about something that is a part of the reflections and refractions and well, quite frankly, Snell's law. So the statement is, according to Snell's law, when light passes from an optically dense medium into a less dense one, N1 is greater than N2, the propagation vector K bends away from the normal. In particular, if light is incident at critical angle theta c equals sine negative or sine inverse N2 over N1, then theta t is equal to 90 degrees. All right, so transmission's at 90 degrees. And the transmitted ray just grazes the surface. If theta I increases or exceeds the critical angle, there is no refracted ray at all, only a reflected one. But the fields are not zero in medium 2. What we get is a so-called evanescent wave, which is rapidly attenuated and transports no energy into medium 2. What in the world? Part A. Show that ET of R of t is equal to E naught t, e to the negative kappa z, e to the I, kx minus omega t, where kappa is at probably what we expect, omega over c, square root n1 sine theta I squared minus n2 squared, and k is equal to omega n1 over c sine theta I. This is a wave propagating in the x direction parallel to the interface and attenuated in the z direction. Part B. Noting that alpha, or equation 9.108, is now imaginary, use equation 9.109 to calculate the reflection coefficient for the polarization parallel to the plane of the incident. All right. And C, do the same for polarization perpendicular to the plane of the incident. All right. We got a longer question I thought. Part D, in the case of the polarization perpendicular to the plane incident, show that the real evanescent fields are E and B as such, okay, where we have Y for the E field and B for the, or X hat, Z hat for the B. E, check that the fields in D satisfy Maxwell's equations. And F, for the fields in D, construct a Poynting vector and show that, on average, no energy is transmitted in the Z direction. Okay, well, first thing up, we got to draw the darn thing, shouldn't we? All right, so here, if we're propagating at some angle to the Z direction, right, and we're incident on a boundary that has between two mediums, we have Ki, the wave propagation vector in the incident direction, and then the transmitted wave, and then we have theta t and theta I accordingly. Okay, that was in the book. So now we can go back and kind of put together all the what means to be parallel and all that kind of stuff. Okay, so part A, when we're dealing with oblique incidences, ET is equal to E naught t e to the kt dotted with r minus omega t. Okay, clearly our focus is on the propagation vector t sub t dotted with the r vector. So here we know that we set up something to where for the oblique incidences, sine theta t is the x direction and cosine theta t was the z direction. Okay, since we're up to the theta, since z is the horizontal, and that's where we're aiming, that's where we attended our theta to. Whatever, go back to the diagram if we're lost. And what we see is that r is a spatial vector, so x, y, z, and the x hat, y hat, z hat direction. I'm using the angle brackets here because I'm lazy and don't feel like writing out the unit vectors. This is not the time average. So once we take that, we're only left with a x and z component, hence the kt x sine theta t plus z cosine theta t. Now from this, we can go ahead and plug in what we know about the cosine theta t, which was that given? Don't remember if that was given. But we know from above, from beforehand, that cosine theta t was equal to the square root of sine theta t minus 1 from Pythagorean theorem, or Pythagorean identity, rather, excuse me. So now we have an equation of that we can solve for sines only. So that's what we're going to do. Hence here, what we see is that we have kx plus I kappa z, okay? Since that's what we need to set it equal to, where k is equal to kt sine theta t, and then we see what that's equal to. And then kappa is equal to kt, and then sine squared theta t minus 1. Push everything through as we see there. So after that, what we notice here is that we're pretty good. We just got to be careful of how we construct anything further, since we know that we're going to have to deal with that imaginary part. With that, however, we know that we can substitute back in the kx plus I kappa z and simplify everything down the way we expect. So that's where we get the e naught t, e to the negative kappa z, e to the I kx minus omega t at the very bottom. Again, these definitions get so burdensome to deal with that we just kind of carry them along, but they're all stated earlier in the chapter. So for part B, the reflection coefficient is where beta is real and alpha is purely imaginary. Say alpha is equal to IA, with A being some real number. Then we know that the modulus squared of the ratio is equal to alpha minus beta, alpha plus beta squared. Take the complex conjugate, so that's IA on the left-hand side and negative IA on the right-hand side. So distribute, factor, cancel, whatever we got to do, simplify it down. You see we get a squared plus b squared over a squared plus b squared, which of course is equal to 1. So indeed, everything is reflected. Further, from problem 9.17, we saw that E naught R is equal to the modulus of 1 minus alpha beta, 1 plus alpha beta, times E naught I. So with the reflection coefficient, then we square this, which is just the amplitudes, or excuse me, the alpha, which is IA, times the complex conjugate, and you see we get two factors here, which again, 1 minus I, 1 plus I in the numerator, 1 plus I, 1 minus I. They cross cancel and we're good. Simplifies to 1, again as expected. And D, again from problem from problem 9.17, the transmitted wave is given as such, E of t and B of t. And from A, we see that kt dot r is equal to kx plus I kappa z. Sine theta t is equal to ck omega nt, or n2. Cosine theta t is equal to I ck over omega n2. And choosing the phase constant so that tilde E naught t is real. We see here that we plug everything through, and thus we're left with the electric field is equal to E naught, E to the negative kappa z, cosine kx minus omega t in the y hat. Again, we're just picking everything to be real, since that's what we're curious about. Similarly for BT, we can plug a lot of things in. Okay, so in the red, we correspond that with the C over N2. The purple can be pushed to the real part of, since that's all we want is, well, rather the purple can be expanded into cosine and sine from Euler's identity, and then distributed with the parentheses on the right. So you see purple goes with cosine and the I sine. We can't take the real part yet because we need to distribute that with the parentheses and the I kappa, all that gross stuff. But you see the red substitution for V2, which was C over N2, cancels out with the factor of C that we factored out from the parentheses, and the factor of N2 that we also pulled out from the parentheses above with the X hat, Z hat. Okay, so simplify that all down to the real parts only, and we get B is equal to E naught over omega e to the negative kappa z, bracket k cosine, kappa sine. So everything's checking out so far. So part E, we have Maxwell's equations that need to be verified. So divergence of E, does it equal 0? Sure it does. Has that E field has nothing to do with Y. What about the divergence of B? Well, we do have an X, we do have a Y. Let's see if they can consolidate. And if we look, we have we have factors that cancel. We have a K and kappa in both, and e to the negative kappa z in both, and a cosine in both. So that negative sign from the negative kappa does indeed cancel them out. We're good to go. Now, Faraday's law, we got to take the curl. And so we're only left with one part, or rather one component from the electric field, which is namely in the y direction. So then we're left with the partial of EY with respect to Z and the X hat, and then partial EY with respect to X and the Z hat. Nothing too extraordinary there. Take the derivatives, simplify it down. Now we have to take the time derivative of B, and let's see if that works out the same. Simplify. We see we get a cancellation of the negative omegas, and sure enough, the negative time derivative is equal to the curl, so we're good. And what about the Ampere-Maxwell law? Well, we get the curl of B. Again, we only have a BX and a BZ component. So with that, take the cross product or the curl. You see we get partial BX DZ minus DBZ over DX and the Y hat only. So let's go ahead and take these derivatives. Is there anything we can simplify? Well, yes, of course, there always is. You see both terms have an E naught omega over e to the negative kappa z. Pull them out. You also see that both have a sign, and now with the derivatives, both have a kappa squared negative and a k squared. So you can pull a sign off of both of them to the right, all in the y direction, highlighting that in blue. We see that the blue, k squared minus kappa squared equals omega over c squared by the definitions given in the problem. And you see that the N1 sign i's cancel. We like that, plus N2. So now we just have N2 omega over c squared, which is equal to omega squared epsilon 2 mu 2 from c and N2. So good to go on that one. Let's see what else we can do. Okay, so now we plug in that part, and we see that epsilon cancels, or excuse me, the omegas cancel, and we're left with epsilon 2 mu 2 omega e naught e to the negative kappa z sine kx minus omega t in the y-hat direction. All right, now what we need to do is see if that is equal to 1 over c squared, the time derivative of the e field. So the 1 over c squared goes to mu 2 e2, or epsilon 2, excuse me. And then let's see what the time derivative yields. We get a negative on the omegas, so we can factor an omega out from the time derivative. It's in the y-hat direction. Sure enough, this is equal to the curl of B. Good to go. Next is this annoying Poynting vector, which is the cross product of E and B. Notice that when we do this, we can factor out a factor of E and E, or E naught, and e to the negative kappa z. 1 over mu 2 just stays there from the Poynting vector, and I believe the b had an omega or an omega factor. So we factor them all out of the determinant beforehand, so we don't have to copy and paste them every time. It'd be quite cumbersome. Also a nice trick to help with the calculations. Nonetheless, carry it through, do the cross product, and you see we get an x and a z hat component there. Again, that's the direction it's propagating. Kind of makes sense. So averaging over a complete cycle using cosine squared equal 1/2 and the product of sine and cosine equals 0, we see that the x hat direction is the only direction where energy is being propagated over the average cycle, or averaging over the complete cycle. So on average, then, no energy is transmitted in the z direction, only in the x direction, parallel to the surface. What a remarkable result, and there are several papers on this that are actually quite interesting. Definitely pique your curiosity and maybe talk about how they discovered it in the first place. I'll link them below. Definitely worth another read.